Hello, everyone. My name is Abdurrahman from the University of Washington, and I'm going to present my poster on the orbital angular momenta of fission fragments within TDS-LDA. Since there's a lot of information here, and I only have 5 minutes to cover it, I'm going to skip a few parts, but please come talk to me during the symposium if there's anything that interests you here. So, key ideas. First, what's the relevance of this project? Why is it important? Well, nuclear fission has been understood since 1938. It was explained by Lisa Meitner and her nephew, Otto Frisch, but it still lacks a complete microscopic description. One of the least understood characteristics, both theoretically and experimentally, are the spin properties of the fission fragments. And these are hugely important for a host of stuff that people are interested in, including controlling the neutron and gamma ray emission spectra, the dynamics of the fission fragments, etc. What is TDS-LDA? TDS-LDA is currently the only microscopic theory that is both time-dependent and explicitly includes pairing in the equations of motion. And this is interesting for reasons listed in this why TDS-LDA versus alternatives section. Okay, key results. First of all, there is an assumption we're making, which is completely valid for californium-252 and a good approximation for uranium-236 and plutonium-240. Namely, the total angular momenta of the system is the sum of the angular momenta of the fission fragments and the orbital angular momentum between them. The assumption we're making is that the total angular momenta is small enough that we can say that the orbital angular momenta equals the sum of the fission fragments' intrinsic angular momenta. For californium, again, this is perfect because the compound has 0 spin. For plutonium and uranium, it's not much higher, and relative to the values of the orbital angular momentum and the intrinsic spins, it's significantly lower, so it's a valid approximation. And this is the key thing that's interesting. If we make this approximation, we get this selection rule or triangle inequality that restricts the values of the orbital angular momenta. Okay, results. This is the first triple projection performed in literature for the 2 fission fragment spins and the orbital momenta. We were able to give some reason for why we expect the lower angular momentum modes for the fission fragments to be suppressed. And this is shown in the suppression of lower angular momentum modes for fission fragments section. Which I can't quite cover, but the key idea here is that most of the suppression is geometric. That if the only correlation you decide to include is this selection rule for lambda, you expect an enhancement of modes closer to the middle and a suppression of modes, lower angular momentum modes and higher angular momentum modes. But please come ask me questions about this. Here's another very important result we got. In phenomenological models, such as the one Freya uses, the current assumption is that if we look at the angle between the 2 vectors, the 2 angular momentum vectors of the fission fragments, we expect it to be completely isotropic. So all angles basically equally likely. We get a completely different result. We get an extremely strong preference for pointing anti-parallel, so the 2 vectors pointing in the opposite direction compared to pointing in the same direction. And we get a preference for the angle to be away from 0 and away from pi. The angle being away from 0 and away from pi is easily explained by just including a geometric factor, which is sine of the angle. And this just accounts for the fact that it's very unlikely to actually have 2 vectors pointing parallel. because there's only, it has a very, it has no freedom in the azimuthal direction. Meanwhile, if you have the angle at a finite amount, you can now rotate one of the vectors, and you can see that a whole host of vectors can correspond to this single angle. The other very nice result here is if you look at their parameterization, which is just 1 plus some function times cosine of the angle. This, I mean, not some function, some parameter. This parameter basically encapsulates the anisotropy of the distribution, which is a fancy way of saying the preference the distribution has for being parallel or for being anti-parallel. So if this is 0, it has, the vectors have no preference and you get something isotropic. If it's negative, they want to point anti-parallel, and if it's positive, they want to point parallel. If we do a fit, what we found out is that this factor is underestimated by 10. Yeah, here I say an order of 10, but I meant to say just underestimated by a factor of 10, which is a huge inclusion that should be added into these models. Okay, very briefly, comparison with experiment. We haven't yet compared these results with experiment because you have to account for neutron and gamma emission, which we can't do in our code. So we have to use an auxiliary code such as CGMF from LANL. But what's interesting here is the black points, which represent the experimental values, seem to be significantly lower than the values that we obtain. But that's just at first look, because what's interesting is that based on using standard CGMF results, neutrons and gammas are expected to remove a ton of angular momenta. And so if you look here, they remove about 4, maybe 5 or so. And if you look at our values with that angular momentum removed, we would be significantly closer to the experimental values. So we expect them to agree well when we implement this stuff into CGMF. All right, thank you. And please, if you have any questions, come talk to me. I rushed because of the time limit, but I'd love to get into more detail with anything here. Thank you very much.